Here we'll do a quick example where we identify the sample and the population in a survey. The question asks, a survey asked 2,000 U.S. households if they currently own at least one pet. The results show that 69% of households do own at least one pet. Identify the sample and the population in this situation. Remember, with a survey like this, the population is the group that we're interested in knowing something about, but it's usually not feasible to study the entire population, so we gather data from a small subset of that group. So, in this case, we're interested in knowing about all U.S. households, so that's the population. Notice that that wasn't explicitly stated, but it's clear from the problem statement that that's what we're interested in knowing about. Because it's infeasible to study all households in the U.S., we take this sample of 2,000 households. We gather data from them, and we use that to draw inferences about the entire population. Here we're looking at the idea of representative samples. So if we're looking to measure something about a population, we want to gather a sample to measure, and we want to make sure that when we do that, the sample represents the population, that it looks similar to the population as a whole. So we'll look at a couple examples here. First of all, to find the average annual income of all adults in the United States, suppose we sampled representatives in the Congress of the United States. It turns out this is not a very representative sample. First of all, the salary for representatives in Congress is set at a fixed number. And that number is relatively high compared to the average income for all adults in the United States. So it's not representative, because if you look at the whole population, there are some people who make very little and some people who make a lot. And in the Congress, there's a fixed value that's unlikely to be similar to the average value of all adults in the US. So it's not a very good representative sample. We would say, no, this is not representative. The second example says to find out the most popular cereal among children under the age of 10, you could stand outside a large supermarket one day and poll every 20th child under the age of 10 who enters the supermarket. It's not clear that there's any bias in this one. This seems like a pretty good way to find an answer to this question. If you poll children coming into a supermarket of the right age group, you're likely to get a pretty representative sample for all children that do this. Now, you may want to pick different areas of the country, for instance. There could be differences depending on where you look, but without going any deeper, it doesn't look like there are any obvious red flags that this would not be representative for all the answers you're looking for. So this one looks fairly good. And the lesson from these is just that when you're gathering a sample, it's important to look for a representative one that's likely to look similar to your population. You don't want a sample that's chosen too narrowly or that's chosen with some sort of obvious bias. This is a simple example that illustrates a way that a sample can be biased. Here, a coach is interested in how many cartwheels the average college freshman can do at his university. 8 volunteers from the freshman class step forward. After observing their performance, the coach concludes that college freshmen can do an average of 16 cartwheels in a row without stopping. Is this sample random and representative? In general, a good sample is random and representative. A simple rule of thumb for deciding whether a sample is random or not is just to think about whether or not every member of the population is equally likely to be selected. If so, there's randomness involved. To decide whether or not the sample is representative, think about whether the sample looks similar to the population. Here, the biggest source of bias that we observe, and bias means that the results will be skewed, is this voluntary response bias. Voluntary response bias means that rather than picking people to ask, the coach asks for volunteers. In this case, people that are able to do more cartwheels are more likely to step forward and volunteer for the study. Because of that, we conclude that this probably isn't a very good sample to do this study. A voluntary response bias also comes into play in surveys that have questions where certain responses are more favorable than others. In this example, we're going to decide which type of sampling is being used in each description. The first situation, we have a soccer coach who selects 6 players from a group of boys aged 8 to 10, then 7 players from the group of boys aged 11 to 12, and finally 3 players from a group of boys aged 13 to 14 to form a rec team. Notice the key here, which is that the coach has divided the group into segments based on their ages. So there's a segment from 8 to 10, a segment from 11 to 12, and then a segment from 13 to 14. And from each segment, the coach has selected several players. So after dividing into segments, the sampling could be either stratified or clustered depending on what happens next. But the fact that we're choosing a couple from each group makes it stratified. If we chose a couple of groups all together, that would look more like cluster sampling. So this first one is stratified sampling. Now generally with stratified sampling, we select the same number from each group. In this case, the coach didn't do that. He selected 6 from one group, 7 from another, and 3 from another. But generally speaking, with stratified sampling, we select the same number from each group. In the second part, there's a pollster who interviews all human resource personnel in 5 different high-tech companies. And this may be hard to see at first, but the fact that this pollster selected 5 companies leads you to think that they looked at all of the companies that were out there and thought of each company as a group, and they selected all human resource personnel from a few of these groups. So by dividing them into groups, again, we can think about either stratified or cluster sampling starting that way. And then because the pollster selected everyone from a couple of groups, that's cluster sampling. If they had selected a few from all the groups, that would be stratified sampling. But the fact that they selected a few full groups makes it cluster sampling. The third one, a high school educational counselor interviews 50 female teachers and 50 male teachers. Notice again that there's a separation of categories, and so the teachers have been separated into male teachers and female teachers. They've been divided into groups, and then from those groups, some have been selected an equal number from each, which again looks like stratified sampling. Next, a medical researcher interviews every 3rd cancer patient from a list of cancer patients at a local hospital. And the key here is that term every 3rd, which is what identifies this as systematic sampling. Systematic sampling is where we have a list like this, and we pick some step like this, like 3, and we check every 3rd, or we could pick every 5th or every 10th. Whatever it is, that systematic moving through the list is what makes this systematic sampling. The next one, a high school counselor uses a computer to generate 50 random numbers and then pick students whose names correspond to the numbers. Notice how there's no division into groups, there's no systematic process. This is the full population of students, and we just select random numbers from that full group. And that's what makes this simple random sampling. That's kind of the simplest version, where we're looking at the full population and using a random number generator to just select without any division into groups or anything else. Lastly, a student interviews classmates in his algebra class to determine how many pairs of jeans a student at his school owns on the average. Notice here that this student is looking for information about the whole school, but rather than looking at a full student list and selecting randomly from them, or selecting every 3rd student, or even dividing them into groups, the student just asks the students nearby, the students that are in his class, next to him, which makes this a convenient sample. In this example, we'll see how to select a simple random sample from a population. The population we're given is a set of 6 quiz scores, and there are 10 students. In this example, we'll draw a dot plot, and we're given data that represents the ages of 30 randomly chosen NBA players. And the first thing we need to do is draw an axis that will cover the full range of the data. So just kind of scanning through, it looks like the lowest value here is around 20, and the highest value is about 36. So let's make sure our range will at least cover those values. Let's draw an axis here with values from 20 up to 36. Now that we have our axis, all we need to do is read through each of these data points and put a dot for each one. So for the first value at 22, we just put a dot above the 22. Then we have 28, so we'll put a dot at the 28. Notice it hovers a little bit above the marker, but it doesn't really matter how high we put them as long as we place them at consistent heights, just so we can visualize the final result. That'll make more sense as we draw more of these. The next value is at 20, then at 24, then at 26, then 21, 27, and then we get another 28. So this is the second time we've seen 28. So we won't draw the second dot at the same place as the first one, but we'll put it right above it. So now there's a second dot at 28. Then we go to 31 and 29 and just continue on entering these. We hit another 24 here, and again we just put this one above the first one at that location. Then we have another 22, another 21, then a 25, another 22, another 25, 30, another 29, another 20, and so on. There's our 36, another 24, the first 23, another 36, another 24, another 29, and we'll just finish this out. So there we see our dot plot, where each time we run into a value we've already drawn a dot for, we just draw a one a little bit higher. So notice that the height of these stacks tells us how frequent an age is. So the more frequent ones are over here, and then the 36s, there's kind of what we would call an outlier. They're far out from the other data points. And for instance, 30 is relatively rare. There's only one of those, and so on. So there's a lot we can tell from this plot, and we'll draw other types of plots later on that fit this same kind of pattern of looking for where the data is clustered and where it's spread out. But a dot plot is a very simple way to observe that at first.
Here we're going to build a simple frequency table. The problem states that 19 people were asked how many miles to the nearest mile they commute to work each day, and their responses were recorded in this data set. The frequency table lists each possible data value and the number of times that data value occurs. So we put two columns like this, one for the data values and one for their frequencies. Now we'll go through the data set, and for each unique data value that we see, we'll list that in the left-hand column. Once we've filled in all these data values, now we just need to count how many times they occur. So, for instance, I noticed that 2 appears twice in the data set, so it has a frequency of 2. 3 appears only once, so it has a frequency of 1, and so on, and I fill in the rest of the table. And it's really as simple as that. Once we've filled in the frequency table, a quick check that we can do is add up all the frequencies, and they should add up to how many data points we have. And here, if we add up these frequencies, we do find a total of 19.
In this example, we'll build a frequency table for categorical data. We're given a sample of NBA players with their position, which is a categorical variable. It divides them into categories: point guards, shooting guards, small forwards, power forwards, and centers. And we're going to build a frequency table to go along with this. So the categories will be the divisions, and then we'll count the frequency in each category. So our frequency table will start with 2 columns, one for the position and one for the frequency. And then we'll add a third column for relative frequency. It's a good thing to include when you draw a frequency table. It's not entirely necessary every time, but it's a good idea to include it when you can. So the positions, we have point guard, shooting guard, small forward, power forward, and center as our 5 categories. And then we just go through and count how many there are of each one. So for point guards, for instance, we have 1, 2, 3, 4 of them. So the frequency is 4. For shooting guards, you can count 1, 2, 3, 4, 5, 6, 7, 8, 9. For small forwards, we have 1, 2, 3, 4, 5, 6, 7. For power forwards, we have 1, 2, 3, 4, and 5. And then for centers, we have 1, 2, 3, 4, and 5. And notice that if we add up those frequencies, we should get the total number that we have, which is 30. So we should get 30 if we add those up, and you can check that by adding those frequencies. For the relative frequency, we need to divide each frequency by the total number that we have in our sample, which is, again, 30. So for the relative frequency of point guards, we would divide 4 by 30. which we could write as a fraction, or if we wanted to, we could write that as a decimal, which comes out to about 0.133 or 13.3%. Then for the next one, we would divide 9 by 30, which works out to 30%. 7 out of 30 is 23.3%. And then 5 out of 30 is about 16.7%. And that's for both of the last two categories. So again, a frequency table is pretty easy to construct. All you have to do is count how many fall into each category. And in this case, the categories were the positions of the players. Here we're going to build a grouped frequency table using the data set of NBA players with their points per game shown below. So we have 30 values ranging from 1.4 up to about 24. And we're told to use a class width of 5 for our grouped frequency table. So we want to start low enough that we can cover all of them. And rather than starting at 1, let's start at 0 just to get a nice round number and make it easy for ourselves. So in our frequency table, the first column will be points per game. And our first category, the first class, will start at 0. And we'll go up to 5. But remember, we won't go all the way to 5 because we don't want to overlap our classes. So the first one's going to go up to just less than 5. Let's use 4.9 to represent just less than 5. And then the next one will start at 5.0 and go up to 10, but just below 10, so we'll stop at 9.9. And then we'll go from 10 to 14.9, 15 to 19.9, and 20 to 24.9. We don't need any more classes because that's as high as we need to go to cover everyone in this data set. So the next column will be the frequency, and then lastly we'll have the relative frequency. Since there are 30 values here in our data set, once we have the frequencies, we'll just divide each one by 30 to get the relative frequency. We won't show this in detail for all of these classes, but just for the first class, from 0 to 4.9, we'll go through and select all the ones that fit into that category. So between 0.0 and 4.9, in the first row, we find 4.9. In the second row, we find 1.4 and 2.0. And in the third row, we find 3.0, 4.3, and that looks like all of them. So there are a total of 5 that fall into that range. And then we can continue this on for all the others, but I won't show the counting. You can go through and do that yourself, and I'll show you the results here. So once you count all the others, you should get 11 for the second class, 5 for the third class, 4, and then 5 for the final class. And then if we divide each of these by 30 to get the relative frequency, 5 divided by 30 is 0.16 repeating, so you can round that to 0.167 or 16.7%. And then 11 out of 30, we could round to 36.7%. 5 out of 30 again is 16.7%. And then 4 out of 30, we could round to 13.3% to get the relative frequency for each. So it's really just counting. The only thing to keep track of for grouped frequency tables is to make sure your classes are all evenly wide and that none of them overlap. That's the important piece. Here we'll build a histogram using the data set for the players in the NBA with their points per game listed here. In the last example, we built a grouped frequency table, and now we're going to build a histogram that matches it. So we're going to take the frequency table we built earlier and just draw this histogram to represent the same picture. So to do that, we'll start with a grid, and the x values will range from 0 up to 24.9 or up to 25. So we'll have 0 here, 5, 10, 15, 20, and 25. And each of these classes will fit between two of those values. So the first class goes between 0 and 5, the next one goes between 5 and 10, and so on. And of course we know that it goes just up to 5, but not including 5, and so on. But we'll draw it as if it goes all the way to 5, just to make the picture as simple as possible. Then on the vertical axis, we have the frequency. So here we have the points, here we have the frequency, And the highest frequency we see is 11, so we need to at least go up to 11. So let's have 10 here, then 5. And then we just draw a bar to the right height for each category. In the first class, the frequency is 5, so we'll draw a bar up to 5, ranging from 0 to 5. Then from 5 to 10, the frequency was 11, so that one goes all the way up to the top of the graph. Then from 10 to 15, that frequency was again 5. From 15 to 20, it goes down to 4, so we'll draw it a little shorter, down at the tick mark for 4. And the last one goes back up to 5. So each class, each category, gets a bar with the height representing the frequency. It's relatively simple once you've drawn the frequency table, which just consists of counting the ones that fit into each class. Here we'll build a bar chart for this data set, which is the positions for the players in the NBA sample. Again, we have 30 observations falling into one of 5 categories: point guards, shooting guards, small forwards, power forwards, and centers. First, we need to find the frequency of each category, which means building the frequency table. But since we've already done that in a previous example, I won't go through in detail and count those. Rather, we'll just put the results here in this frequency table. We have the 5 positions and the frequencies. There are 4 point guards, 9 shooting guards, 7 small forwards, and 5 power forwards and 5 centers. Now, just like with the histogram, we start with our grid, and this time the horizontal axis will represent, again, our categories. So we'll have 5 spots for our bars to go. And then the vertical axis will again represent frequency. So the horizontal axis is position, the vertical axis is frequency. The highest frequency we see is 9, so we need to make sure we go up to at least 9. Let's again go to 10. And now we're ready to draw a bar for each position. So rather than having the bars connect like they would with a histogram, with a bar chart, since we're thinking of these as separate categories, they're not ones that flow into one another, we'll draw the bars with some separation. So at the point guard position, we'll draw a bar that goes up to 4, since there are 4 of those. And then at the shooting guard position, we'll draw one that goes up to 9. Small forwards have a frequency of 7. And power forwards and centers each have a frequency of 5. So again, we're drawing a bar where the height represents the frequency of that category. But unlike with a histogram, these bars are separated because we're indicating that these are separate categories and there's not a flow from one to the next. Let's build a stem and leaf plot. The question says, suppose you gathered data on how long it took you to get ready in the morning. For 40 days, you measured the amount of time between when your alarm went off and when you left the house. The results are below, rounded to the nearest minute. And we want to build a stem and leaf plot for this. For a stem and leaf plot, we divide each value into its stem and its leaf. And the stems are generally the tens place, although you can tweak this and make it, for instance, the ones place. But in this case, since our values are 2-digit values, the first digit will represent the stem and the second digit will represent the leaf. So if you look through, you'll notice that all of these numbers start with either 1, 2, or 3. That's the first digit. So our stems could be 1, 2, or 3. And now we'll go through, and for each value, we'll place that leaf in the correct category. So the first value is 35, so we'll put a 5 under the leaves category in the third row. Then for 28, we'll put an 8 here. Then 25, we'll put a 5 here. Then 23, and so on. We'll put another 3. Then 32 means we'll put a 2 in the third column. Then 29, 19, 21, 13, and so on. And I won't go through and fill all these out in detail. I'll go through and show the final result in just a moment. Now what you often find with a stem and leaf plot is that we write the leaves in the order of their value rather than the order in which they appear in the dataset. So instead of writing 8, 5, 3, 3, 9, 1, we would write the 1 first, and then the 3s and the 5s, and so on. Now this takes some extra work because we have to do some sorting, but when I show the results in a second, it'll be shown in that way with them sorted by value. Now that we have all the stems and leaves written, notice how it looks. It looks almost like a histogram or a bar chart turned sideways, where the length of each string of leaves represents the frequency of that category. So it divides it into categories by tens, and we can see that the most frequent category is the range from 20 minutes to 29 minutes. And yet, unlike a normal grouped frequency, by grouping them, we haven't lost any information. We could reconstruct the entire data set from this stem and leaf plot if we had to. In this example, we'll construct a scatter plot for some data that we're given. We're given the sizes of several TVs and the price that goes along with each one. Now our data is separated into 3 categories just so that the table could fit easily here, but side by side you'll see a size and a price where the size is given in inches and the price is given in dollars. And we want to construct a scatter plot where we compare these 2 variables. Now when we construct a scatter plot, we have to pick which variable will be x and which one will be y. It's not crucial that we pick it in the right order because it turns out if they get switched, much of the analysis we can do is still the same. But if we can, it would be nice to pick x and y in a reasonable way. And usually we want to think about how x determines y. In other words, is there one of the variables that seems to control the other one? Would we say that the size determines the price of the TV, or would we say that the price determines the size? It's probably more likely that we would say that the price depends on the size, or that the size determines the price. So we could call x the size and y the price. So let's say our x-axis represents size and our y-axis represents price. Again, we'll try to be consistent with these where the first column is x, the second column is y, but it turns out that if you switch the order, it doesn't change too much, at least at this point. So now we need to put a scale on each axis. So for the sizes go up to about 60 inches. So let's make sure we include at least up to 60. Let's say we go up to 70 here. And if we start down at 0, that means we need to divide this evenly so that we get to 70. So halfway there would be 35. And then if we divide these by 5s, 3, 5, 10, and so on. Then the prices range from 200 to about 2,800. So let's say we include all the way up to 3,000. And let's mark it in increments of 500. Now for each value in our list, let's take the first one for instance. The size is 43 inches, the price is $500. So on the horizontal axis, the size axis, we'll go up to 43, which is around here, between 40 and 45. And then on the price side, we'll be right at 500. So we want to find out where those two cross, which is right around here. So our first point will be right there at 43 inches and $500. For the next one, we'll go to 55 at $900. So 55 is right here between 50 and 60. $900 is right here, right under 1,000. So those two look like they cross right around here, which gives us our second point. And then we'll continue for the rest of them without showing each one in detail. I'll just show the final picture here in a moment after we've drawn all these points. So there's the final result, and even though it's hand-drawn and imperfect, we can see the general trend, which is that larger TVs tend to cost more. So there's this general upward trend as you scan through this picture. And that's really the value of a scatter plot, is to look for an association or a connection between 2 variables to see if there's a relationship. And this one looks like there's this upward trend. Later on, we'll talk about how to draw a line or some other curve that represents this shape. But for now, just notice that there's that relationship between the two. Find the median of the salaries listed below. So these are the salaries from the MBA data set. We have 30 values, and we want to find the median. Remember that the median is the middle data point. Now, helpfully, these salaries have been listed for us in order from smallest to largest. So notice we have the smallest value here, and then they increase along this row, and then down to the next row until we reach the largest value at the bottom right. And that's important when you're finding the median, to order them from least to greatest or from greatest to least, so that when we look in the middle of that list, the middle value is truly in the middle between the highest and lowest, so that half of the data points fall below it and half of them fall above it. So since it's listed like this for us, we can look halfway through. Since there are 6 rows, at the end of the 3rd row and the beginning of the 4th row, we have the middle. So the middle is right between this value and this value. Since there are 2 values in the middle, which will happen every time we have an even number of data points, we need to find the number halfway in between those two, which we do by averaging them together. So find the average of those 2 numbers in the middle, that will be the median. If we had an odd number of data points, like say we had 29 players, we would find the middle value and that would be our median. We wouldn't have to find any average. But anytime there's an even number, there will be 2 in the middle, so we need to find whatever is halfway in between those 2. So the median will be halfway between 4,469,160 and 4,767,000. So if we add those together and divide by 2, what we get is 4,618,080, and that's the median. Half of the players make less than 4,618,000, half of the players make more. So that's the middle data point, and it's a good measure of the center. Here we'll find a weighted average using a student's score in a class. So we have several assignments, 3 tests, homework, project, and final exam, and we're given the student's score on each of these assignments, as well as a weight for each assignment or a number of points for them. Now notice that usually we'd be given either the weight or the points. In this case, we're given both, and if you look closely, there are a total of 1,000 points that they could earn. If you add up all those points, you should get 1,000. And if you divide each of those point values by 1,000, you'll get the percentages that are listed here. So really, the same information is given in the weight column or in the points column. And you may see for some of your classes, the scores are given with weights. Sometimes they may be given with points. It's really the same thing. It's just written in a different way. So we're going to show the calculation with both just to compare, but we'll get the same answer either way. For part A then, let's use the weights. So for the weights, we can multiply each score the student got by the weight that's associated with it. And once we multiply those and add them all together, the answer we'll get at the end is the average score. So the weights are nice because they're already scaled for us, so that just by multiplying the score times the weight and adding those together, we'll get the final weighted average. So all we have to do is take 85% times 20% plus 92% times 20% plus 87% and so on. So if we multiply all those and add them all together, the answer we get at the end is about 0.899, which works out to 89.9%. So on a standard 10-point scale, this student will be very close to an A, just under 90%. Now let's do the same thing with a point system. And we're going to get the same answer, of course, but this time we have to do 2 steps, where first we multiply their score. So for the first category, they got 85% times the number of points they got, and then do that for all of them. And once we multiply and add all those up, we get 899 points. So they earned a total of 899 points, and then when you divide that out of the total of number of points they could have earned, which was 1,000, they get 0.899, which again works out to 89.9%. So notice you're doing the same work both ways. It's just that when you use the weights, you've already divided by 1,000 before you start. When you use the points, you have to divide by 1,000 at the end to get the final score the same way you did with the weights. So either way you do it, you're using the same values, and this is how you do a weighted average, whether you're given the weights as percentages or as points out of a total that you could earn. Here we'll find the mode of a data set that's summarized for us. We're already given the frequency table rather than just the raw data, so most of the work is done for us. The mode is the most frequent data value. And the nice thing about having the data given to us as a frequency table is all we have to do is look through the frequencies and find the highest frequency. Notice the highest frequency is 4 and occurs 3 times. There are 3 values which occur 4 times and are tied for most frequent, and those are 21, 22, and 24. So there are actually 3 modes, and this can happen a lot. In our case, the modes are 21, 22, and 24. Here we'll find the range of a data set that we're given, and the data set is the heights of the players given in the NBA data set. The range is really simple. It's just the difference between the smallest and the largest. So all we have to do is look through this list and find the smallest number and the largest number that occur. If you scan through, you should be able to pick out that the lowest number is 1.78. 1.78 meters is the shortest player in the sample that we listed. And the tallest player is 2.13 meters. So the range is just the difference between those two. If we take 2.13 minus 1.78, the range is the difference, or 0.35 meters. That's a really simple way of measuring how spread out the data is. If the range is larger, it's more spread out. If the range is smaller, it's more tightly clustered together. So 0.35, when compared to the values in this data set, is a fairly small range. So they're fairly tightly clustered together. All of these players are relatively tall.
Here we'll calculate the standard deviation by hand using the formula instead of using the built-in function in the calculator, just to illustrate how the formula works. We have 5 data points and we want to calculate the standard deviation. The first thing we need to do is to calculate the mean. So the mean, remember, is the sum of the data points divided by the number of data points. So we add them up and divide by 5, and we find that the mean is 10.2. Now, the standard deviation of this data set is the square root of the sum of the squared deviations divided by n minus 1, and all of that's inside the square root. So we'll need to calculate these things individually. We need to find each deviation, the difference between each data point and the mean, square those, add them up, divide that answer by n minus 1, and then take the square root of that answer. So this can get kind of tedious, which is why we only do this with small data sets. And from this point on, we'll use the built-in function in the calculator, but here we'll just illustrate the formula once. We'll use this table to organize everything. We have the data values listed, and we'll calculate the deviation for each one by simply subtracting this number, 20 for instance, minus 10.2, and then 4 minus 10.2, and 15, and so on. And we'll calculate a deviation for each data value. Once we've done that, we square them all. And remember, the reason that we square them is because if we try to average these deviations, we would get 0, because the positive ones and the negative ones would cancel each other out. But by squaring them, we end up with all positive numbers, so when we average those, they don't cancel each other. Then here all the squared deviations are filled in. Now, we need to add those squared deviations, divide by n minus 1, or 4 in this case, and then take the square root of the answer. Adding these all up, we get 210.8, and then if we divide that by 4, we get 52.7. But we're still not done. The last step is to take the square root of that. The square root of 52.7 is 7.26. So the standard deviation of this data set is 7.26, or the distance that a typical data point is from the center. Again, this example mostly illustrates why we don't calculate the standard deviation by hand usually. Even for a small data set, it gets pretty tedious.
A random sample of 11 statistics students produced the following data, where X is the third exam score out of 80, and Y is the final exam score out of 200. Here we'll use a graphing calculator to find the equation of the least squares regression line, so that we can predict the final exam performance, which is Y, based on the third test score, which is X. So to use the calculator, we first need to enter the data. If we enter the Stat menu and Edit, we can enter the data here, which I've already done. The first list, we've entered the X's, and in the second list, we've entered the Y's. Now, if we go back under the Stat menu, we want to calculate, so we'll scroll over to the Calc menu, and we want linear regression. The form we've been using is this number 4, linreg ax plus b. So a is the slope and b is the y-intercept. If we select that, we don't need to change anything here because we entered the x's in list 1 and the y's in list 2. So nothing needs to be changed. We can just scroll down to calculate, and it gives us the equation. The form of it is y equals ax plus b, and we get the values for a and b, as well as values for r squared and r. And now we have a better sense of what this r represents. That's the correlation coefficient. So the correlation coefficient is about 0.66, which means there's a moderate linear relationship, and it's positive. So there we go. There's our regression line, and there's the r value that goes with it. Here we're given a regression equation, which we developed in a previous example, to predict the price of a house based on its square footage. So if x represents the square footage, we can predict the price in thousands of dollars. So if we entered 1,000 for the square footage for x, we could calculate a value for y that would be the predicted price for houses with that square footage. And we're going to use this equation to predict the price of homes with 2 different square footage values. So all we have to do in each case is replace x with the given value for square footage. In the first case, we have y hat equals 0.099 times 2700 plus 160.8, which works out to 428.1. So that corresponds to $428,100. And that technically means that the average house price we would expect for all the houses that are 2,700 square feet would be $428,000 approximately. And then in the second case, we can make a similar prediction for houses with 4,500 square feet. And that works out to just over 600,000. Then the question asks, which prediction do you expect to be more reliable? Now for this, we'd really have to go back and look at the data, which we don't have in front of us. But if you go back in the textbook and look at the data, you'll notice that in the range of houses that we have data for, 2,700 square feet falls within that range, and 4,500 square feet does not. None of the houses we have in our data set are nearly as big as 4,500 square feet. So it turns out that the first one is more likely to be reliable without extra information. For all we know that now, it seems more likely that the first prediction would be more reliable because we've seen houses that are similar to it in our data set. The first example we call interpolation, where we are predicting within our data range. The second one we call extrapolation, where we're predicting beyond our data range. And in general, extrapolation is dangerous because we don't know quite what could be happening beyond the range of data we've actually looked at. So in general, interpolation is more reliable than extrapolation. So the first prediction is more likely to be reliable, even though we don't have a lot of information about it at the moment. Here we'll do a linear regression problem with several steps. First, we're given some data, which is a set of quarterbacks in the NFL during the 2019 season. And for each quarterback, we're given their height and their weight. We're going to compare these two. Now, without any other information at the moment, we're going to assume that height is going to represent X and weight will represent Y, just because they're ordered that way. Later on in the problem, we might have more information that'll tell us which one should be X and which one should be Y, but for now, we'll just assume that and change if necessary. So first, we want to calculate the correlation coefficient. And to do this, we'll use the calculator. So first, we need to go to the calculator and enter this data. To enter the data, we'll hit the Stat button and hit Enter to get into the Edit menu. And under List 1, we'll enter the X values. So the heights that we saw, the first quarterback had a height of 75 inches, then 74, 74, 70, 71, 74, 76, 77, 72, and 74. And then we can scroll over to the second list for their weight, and we'll enter these as well. Once we have all the data entered, we can go back into the Stat menu and scroll over to the Calc, down to the Linear Regression option. Again, we've entered X's in list 1 and Y's in list 2, so we don't need to change anything. If those were switched, it wouldn't change the correlation coefficient anyway, so for this first part, it didn't really matter which way we entered them, but later on it will be significant. So we'll just hit Calculate, and it goes ahead and gives us the equation for the line, which we don't need just yet. All we're looking for at the moment is the value of R, which is about 0.6. The first part of the question just asks for the value of R, so now that we have that, we can go back to the notes and enter that. Now for the second part of the question, we want to know, is there a strong linear relationship? So based on the value of R, we know first of all that there is a positive relationship, since R is positive, and we wouldn't necessarily say it's a strong relationship because it's less than 0.8, which again is not a magical number, but it's sort of an agreed upon level for a strong relationship. But 0.6, we might say there's a moderate relationship. And often a moderate relationship is good enough to continue on, and we'll continue to do the rest of the problem. So we wouldn't necessarily say it's a strong relationship, but it is a moderate linear relationship. The next part of the question asks for the regression line, which we've already calculated. Now notice the direction here. The regression line is going to predict the weight from the height. In other words, the weight is going to depend on height, which means that weight should be y and height should be x, which is the way that we already set it up. So it's good that we did so, and the regression line that we got from the calculator earlier is the one that we'll write here. So if we go back to the calculator, we can see what we had there. We have A is about 3.01 and B is negative 4.43. So now that we have that, we can move on to the rest of the problem. Here we want to graph the data as well as the regression equation. And I'll actually use the calculator to do this. We'll graph both the data and the equation on the same window. We already have the data entered, so if we turn on the stat plot under second y equals, we turn on this first stat plot and leave it as a scatter plot the way it is. X and Y are in the right order. Now when we graph, we'll see those points as long as we're scaled to the right window. And then also, if we hit y equals, we can graph the equation, which was 3.01x minus 4.43. Now before we graph, we should go to the window and make sure that our x values and y values are in the right range. The x values, the heights range from 70 up to 77, so we should make sure that x covers at least that range. So let's say we make x min 68 and x max 79. And then the y values, the weights, range from 200 up to 233. So let's say we go from 190 to 240. Now when we graph this, we see those heights as well as the line that passes through them. Now notice what this graph gives us. First of all, it points out that outlier on the lower right-hand side. And that's the first entry. Lamar Jackson is on the upper end of the height scale. He's at 75 inches. He's one of the taller players, but he's actually the lightest of all of them at 200 pounds. So if we actually removed him from the data set, our R value would be much, much higher because he's what's making the data points not follow a straight line. Since he's kind of out in space by himself, that messes up some of the strength of the linear trend that would be there otherwise. So sometimes there are outliers like this that will lower the value of R, but if you remove them, the value of R will be better. Of course, you can't just throw away outliers because your data would look better without them, but keep that in mind. Next, we can predict the weight of a quarterback who is 73 inches tall. So given a height, we can predict their weight using this equation. So A is 3.01, and then if we plug in 73 for X, we can predict that Y hat, their weight for a quarterback of this height, would be about 215 pounds. Lastly, we get this question. Does Drew Brees weigh more or less than the weight predicted by the regression line based on his height? So we can do the same thing we did in the last part, where we predict what someone who is the height of Drew Brees, 72 inches, would tend to weigh according to this equation. And according to this equation, that comes out to 212 pounds approximately. So the question asks, does he weigh more or less than the predicted value? The predicted value is 212 pounds, and he only weighs 209 pounds, so he weighs less than what's predicted. So here are the answers to all the parts of this question. We found the correlation coefficient, we interpreted it, we found the regression line and graphed it alongside the data, and then we made a couple of predictions based on that regression line.
The scores on a college entrance exam are normally distributed with a mean of 52 points and a standard deviation of 11 points. And we're asked to find what two scores encompass 95% of the test takers. Since the data is normally distributed, the empirical rule tells us that 95% of the data will be within 2 standard deviations of the mean. Since 1 standard deviation is 11 points, 2 standard deviations is 22 points, twice that. So 52 minus that and 52 plus that will form the boundaries of this range that includes 95% of the data. Therefore, we decide that 95% of the values lie between 30 and 74. IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. Here we're asked to use the empirical rule to find the data that is within 1, 2, and 3 standard deviations of the mean. Remember, the empirical rule states that 68% of the data is within 1 standard deviation of the mean. Meaning that if we go 1 standard deviation below the mean and 1 standard deviation above the mean, that range will hold 68% of the data. 95% of the data falls within 2 standard deviations. And almost all the data, or around 99.7% of the data, falls within 3 standard deviations. So if we work from the mean down 3 standard deviations and up 3 standard deviations, will encompass almost all the data. In this case, with a mean of 100 and a standard deviation of 15, 1 standard deviation below will be 85, and 1 standard deviation above will be 115. 100 minus 15, 100 plus 15. So 68% of the data, in other words, 68% of people will have an IQ score between 85 and 115. 95% of people will have an IQ score between 70 and 130, and almost everyone will have an IQ score of between 55 and 145. Here we have a picture that illustrates this situation, where each unit on the axis is 1 standard deviation. Suppose you know that the prices paid for cars are normally distributed with a mean of 17,000 and a standard deviation of 500. We want to use the 68, 95, 99.7 rule, or the empirical rule, to find the percentage of buyers who paid in any given range. The first thing to do when working with a problem like this is to draw a picture. And here's the picture for this example. The center is the mean, and then each unit on the axis is the standard deviation. So we have it centered at 17,000, we go up to 17,500, 18,000, 18,500, and we could keep going, but that's all we need. And then on the lower side, we go down to 16,500, 16,000, and 15,500. Here I've also filled in all the percentages for each range. Notice that the empirical rule tells us that 68% of the data falls within 1 standard deviation of the mean. Since everything is symmetric, each half of that holds half of that 68%, and that's where those 34% numbers came from. Then I know that within 2 standard deviations of the mean, I have 95% of the data. If I have 68% in the middle, and by going out another standard deviation, I get to 95%, that means the yellow regions together must make up that 27% that gets us from 68% to 95%. So if the 2 yellow regions together hold 27%, each of them holds half of that, or 13.5%. We can repeat this process for the green regions. Again, going out to a third standard deviation, we know that that holds 99.7% of the data. So the green regions together must hold 4.7% of the data, since everything up through the yellow regions held 95, and then just by adding the two green regions, we got to 99.7. The green regions must be that 4.7%. Therefore, each of them holds half of that, or 2.35%. And then outside the 99.7 is 0.3% of the data, and again, because it's symmetric, each half of that, or each tail, contains 0.15%. Again, the goal is not to memorize these percentages, but just to realize how we got them and be able to rederive them at any point. But now that we have them, we can use them to solve the problem. So, part A asks what percentage of buyers paid between $16,500 and $17,500. So we find those 2 points on our picture, and between them, we add up the blocks and find that 68% of buyers were in that area. Similarly, for part B, between 17,500 and 18,000, we locate those points, and between them, there's just one region with 13.5%. For part C, we look between 16,000 and 17,000, and there's 2 blocks there. Adding them up, we get 47.5%. For part D, we're looking between 16,500 and 18,000, and adding up those 3 blocks, we get 81.5%. So 81.5% of people paid somewhere between $16,500 and $18,000 for their car. Part E asks what percentage paid below 16,000. So that's right here. And below 16,000 we have 2 blocks to take care of, 2.35% and 0.15%. Adding them together we get 2.5%. So 2.5% of buyers paid less than $16,000 for their car. Lastly, the final part asks what percentage paid above 18,500, and again there's only 1 block up there, so 0.15% of buyers paid above that amount. And here we have all the answers summarized. Here we're told that female adult height in some population is normally distributed with a mean of 65 inches and a standard deviation of 3.5 inches. And we're asked to find the z-scores of 2 heights. Remember that a z-score is the data value minus the mean divided by the standard deviation. And this z-score represents how many standard deviations this data point is above or below the mean. If the z-score is positive, it's above the mean. If the z-score is negative, it's below the mean. For the first example then, to calculate z, we take 58 minus the mean, 65, and divide by the standard deviation, 3.5. 58 minus 65 is negative 7, and that divided by 3.5 is negative 2. So what that means is that first data value is 2 standard deviations below the mean. For the second point, we do the same thing, now taking 71 minus 65 and dividing by 3.5. 71 minus 65 is 6, and that divided by 3.5 is 1.71. So the second data point is between 1 and 2 standard deviations above the mean. Scores on an IQ test are normally distributed with a mean of 100 and a standard deviation of 15. We're asked to find the IQ score that corresponds to each of the following z-scores. So here we're given z-values, and we're asked to work backward from them to the data values. Again, remember though that a z-score is simply a given data value minus the mean divided by the standard deviation. Here we're given a z-score, the mean, and the standard deviation, and asked to solve for the data value. For the first one, for example, we know that z is negative 1.5. The data value is the unknown part that we're going to find. So the z-score is x minus the mean, 100, divided by the standard deviation of 15. Now to solve for x, I'm going to multiply both sides by 15, and we find that negative 22.5 equals x minus 100. Then add 100 to both sides to get x equals 77.5. So a z-score of negative 1.5 corresponds to an IQ score of 77.5. For part B, we do the same process. The z-score equals the data value minus the mean divided by the standard deviation. So we multiply both sides by 15 and find that 30.75 equals x minus 100. And then adding 100 to both sides, x equals 130.75. So a z-score of 2.05, or just over 2 standard deviations above the mean, corresponds to an IQ score of around 130. This question asks, what is the margin of error on a poll with a sample size of 1,000 people? With the simplifying assumptions that we've made, the margin of error is 1 divided by the square root of the sample size as a percentage. So this will give us a decimal, and then we'll write it as a percentage. To do that, some people write that this times 100% is the margin of error. And that times 100% just converts that decimal into a percentage. Again, there's some simplifying assumptions that lie behind this, but for our purposes, this is good enough. In this example, n is 1,000, so the margin of error is 1 divided by the square root of 1,000 times 100%. 1 divided by the square root of 1,000 is 0.0316, etc. And by multiplying by 100% or converting to a percentage gives us 3.16% approximately. It's fairly common for a poll to have a margin of error of around 3%, and when you see that, you can tell that the sample size is around 1,000 people.
In this example, we're going to find the sample size that corresponds to a given margin of error. So if we want a poll to have a margin of error of 2% or less, what's the minimum sample size needed to make that happen? Remember, the margin of error looks like 1 over the square root of n as a percentage. So we can write times 100% just to indicate that we're making it a percentage. So if we want this to equal 2%, then really what we want is we want 1 over the square root of n to equal 0.02. So as a decimal, we want 1 over the square root of n to equal 0.02, or as a percentage, we want it to equal 2%. Now we need to solve for n, and it takes a little bit of algebra to do so. There are a few ways to observe this. One, if we want to get n by itself, we could move it out of the denominator by multiplying it on both sides. So if we multiply it over there, we get 1 equals 0.02 times the square root of n. And then, again, we're trying to get this part by itself, so we'll divide both sides by 0.02, which gives us 1 over 0.02 equals the square root of n. Now, there's a shortcut to this. At this step, you could say we have 1 over the square root of n equals 0.02. You can actually flip both sides of that equation upside down and get square root of n over 1 equals 1 over 0.02, which gets you to the same place that we already did, just by a shortcut. Don't get too lost in that step if that doesn't make sense, but there are shortcuts to some of this algebra. Once we get to this point, though, we just have one step left, which is that we need to square both sides. Now before I do that, I'm going to simplify 1 divided by 0.02, and that simplifies to 50. But now to get rid of that square root, we just need to square both sides. And the square root will cancel each other. When we square 50, we get 2,500 equals n. So that's our answer, that if we sampled at least 2,500 people, we would be guaranteed to have a margin of error of 2% or less. And if we sampled more than 2,500, our margin of error would be less than 2%. But as long as we sample 2,500, we'll be guaranteed to have a margin of error of 2%.